so we're down to Chapter 7, Analyzing Malicious Windows Programs. And let me bring this up. All right. So, this is a summary of how Windows works. All right. So the Windows API, if you have Windows software, it runs in userland. It does not have direct access to the hardware. So in order to do anything like put a window on the screen or read the keyboard or do anything to do with hardware, it has to ask the API to please do that for me. The kernel is written by Microsoft mostly, although there are device drivers from third-party companies in there, and you have to ask it to please please put something on the screen, please read the keyboard, please send some network traffic out, that sort of thing. So here's some concepts of how the Windows API works. It has its own names to represent data types, like DWord for 32-bit and Word for 16-bit integers, and it has this thing called Hungarian notation. It will put a abbreviation, a couple of letters before variables to show what they are. So you'll have
double word, right?
Yeah, double word. Yep, word and double word, and then handle and long pointer, and you'll see these abbreviations in the names of things, which are used to indicate the type of data stored. And so there's handles. Now a handle is basically a pointer to an object, and what it is a way to refer to an object you created, an object of a software representation of something like a window or a process or a network connection. All these things return handles, and then you can do an action on them, like you can send data out the network connection, you can resize the window or close the window, and that's what happens. When you do anything that creates an object, you get a handle. Okay, and all right. And so you create window EX function. By the way, this EX at the end means extended. This is very common. So Microsoft's had a version of this API call in an earlier product like Windows 95, and then when they modify it, it gets an EX to be extended. And sometimes EX, EX, EX. Many versions have been through. And so you run this thing to create a window. It returns a handle to the window. And if you want to do something later like close the window, you use that handle to tell it which window you're talking to. So same thing, if you create a file, read file, write file, create file mapping, map view of file. Now these are normal things the person would use, read a file, write a file. These creating a mapping and map view of file directly loads a file into RAM, which is not a normal activity. That's something malware would do. You load a file into RAM sheet and then execute it as a program. Normally you let the Windows loader do that. You double click on an exe and it loads. But if you make a product like UPX, a packer, then it has a custom loader that loads the product into RAM, unzipping it first. So it would probably use these kind of API calls to do that. Where instead of using the standard process you actually create, you allocate a region of memory and then manually copy a disk file into there, because you're doing something other than normal running of a program. Now there are special files. Like you probably know in Microsoft Windows networks, you can do / server. And that will get you to a server with that name, or you can even put an IP address in there. It'll open a server at that IP address. And then you can access a shared folder this way. That's one way to do it. But if you do it this way with a question mark, then it allows you to have longer file names. It's more directly related to the hardware. This is like in Linux. There are...
Is it wildcard?
It's not a wildcard. It's a special symbol to refer to mapping from the root of the entire file system, from the root of where all objects live. So this is like direct disk access in Linux, as opposed to access through a volume. So yeah. So anyway, here's special. This is the lowest namespace is /. This is the device namespace for direct disk input out with a dot there. So this is what you do to corrupt the disk. You write to the physical disk, and then you can access the reserved parts of the disk, like the file allocation table and stuff. If you open the volume with a drive letter like C or D, you only get the usable part of the disk. You don't get the structure part of the disk, where it stores the volume information, like how many partitions there are, and the fundamental table that stores where all the files are stored. If you do it this way, you can actually physically access the whole disk. So it's something you would do to make like a forensic image of a disk. It's not anything you would normally do to read or write a file. So that's another indication. If you find software writing to the things with this / and a character and another /, that's very unusual. That's some kind of direct access to hardware instead of going through the normal calls that let you do what you normally want to do with the hardware, like read a file and write a file, but not overwrite the master boot record. This is very suspicious if you're doing that, just like it's pretty suspicious if you're loading a file into memory this way with create file mapping. That's another strange thing you would not normally do. You're not opening a file for any normal purpose. You're doing something very weird. So that's suspicious. All right. And so there's also alternate data streams. This is actually a rare thing. It is something added to Windows for compatibility with Apple, because Apple first had music. And when you have music, you have the actual WAV file or something that has the music, and then you have cover art and album notes. And instead of just having them in different files, they made them all data streams from a single file name. So the single file name referred to multiple streams of data. That's called alternate data streams, and Microsoft has it for compatibility with Apple. So you can take a file, that's what this does here. So I make a file called foo, put some data in there, then I do a directory, and I'll see foo is 4 bytes. Now I echo a lot of data into foo:\bar. You take your file and pretend it's a drive letter. Foo:, then you put another file inside the file. And now this shows you that file is only 4 bytes, but it's lying. There's a lot more than 4 bytes on the other data stream. And there is a way to see, there's a switch/R or something, I forget what it is. You can use Endure to see the actual size of the file. So this is a place to hide data, and there was a time, maybe 15 years ago, when malware would hide in there, and the antivirus scanners didn't know how to scan in there. Now they know. But it is a feature of Windows. You can have multiple data streams from the same file name. It doesn't happen very often. The most common thing I know that does is when you download a file from the web, you get the file on the file name, and Microsoft adds a thing called the mark of the web in an alternate data stream. So it knows this file was downloaded from the internet. And if you double click it to open it, a box will pop up saying, this file was downloaded from the internet, it might be dangerous. That's how it does it. It does it with an alternate data stream. All right, then there's the registry. Now, if you use Linux and you install something like Apache, you install the executable, and then there's like a configuration file. Apache.cfg or .ini or something you use, and all the configuration goes in there. So every piece of software comes with its own text file in its own format to configure it. That's how Linux does it, and that's how MS-DOS did it. But when Microsoft wrote Windows 95, they said, we're not going to do that. We're not going to have configuration files for every program just scattered all over the disk in all different formats. We're going to organize it into one structure called the registry, which is going to be a database for all the customization settings for everything on the box, every part of Windows and every piece of software. That's what this is. It's a database that has all those adjustments. And there's a bunch of ways to automatically launch programs in the registry. There's run keys and a bunch of other ones. So it's a common place that malware uses for persistence. To make it come back when you reboot, it puts a registry key in, which will cause the malware to relaunch. And you can do almost anything with the registry. So the registry has 5 root keys: HT classes root, current user, local machine, users, and current configuration. Those are called root keys. It looks like a drive with 5 folders, but it is not. It is emphatically not. In fact, this is where the thing about Windows is it is extremely disorganized and illogical. Especially if you use mathematics or Linux, you get used to things being logical and clean, and nothing is like that in Windows. Everything is bizarre. There's like 10 different ways to do everything. And so these 5 objects are not even independent of each other. One of them is actually a subfolder of another. It is really strange. So anyway, these things that look like folders are called keys, and you have folders in a folder called a subkey, and you can have a value stored in it. Anyway, you see this and edit it with regedit. So here's the root keys. So the local machine, these are global settings. This is the settings for the current user. Down here are all the settings for all the users. So HKey current user is actually a subfolder of this one, HKey users. They appear separately because Microsoft is very illogical. All right. And so you got other ones here, current config, the current hardware configuration, which includes information that your machine does not know until it boots up. When it boots up, it probes the hardware to see, do I have a hard drive? How much RAM do I have? Do I have a keyboard? What displays do I have? Because for all the machinery knows, while it was powered off, you changed the hardware. You plugged in something. So it probes to see what have I got, and it builds HKey current configuration while booting up to reflect the hardware that it actually has. That's why it's current configuration. Yeah.
The beginning of the booting, when the kernel is looking for the drives, the group,
yeah,
is part of this?
Yeah, that's post. Post is the power on self-test. where it checks to see, what have I got? Is there a keyboard? Is there a hard drive? Is there a floppy? What have I got? Then it tries to, if it doesn't find, if something really important is missing, like a keyboard, it won't even boot it. It'll fail. If it finds this stuff, then it will try to decide which one to boot from. Should I boot from the CD or the floppy or the hard drive? And maybe it'll have to ask the user. And then once it boots up, that information is fed into the registry here, current config. So it knows which hardware we have. Yeah.
Usually, the user will be asked if he, for example, if he or she has two operating systems.
Right,
So you have to
right,
decide which one.
right. Or if you have a floppy or a CD, you might want to boot from that. Yeah, yeah. Or a thumb drive, actually. Yeah. Anyway, so right. So there's a run key, and this is the one I mentioned. This is probably the main one malware uses. Anything, the run key is way down here. H key, local machine, software, Microsoft Windows, current version, run. You get used to these really long paths and navigating through these folders. I found it very confusing at first. After a while, you get used to it. And here's the things that are launching automatically. Adobe ARM, Log Me In, some Java update. All these programs have put something in here, so every time you boot the machine, it'll launch. And so here you have a value that the Java update has got the path to the Java updater. Is why that thing's always popping up in the corner. So that's, and all right, now it turns out this is not the only place you can put in something to run. In fact, there are dozens of places, and they're very hard to find. And Microsoft does not give you any tool that shows you all of them. But SysInternals does, which Microsoft bought. So, and this tool will actually find most of them. I don't think anybody can really claim to find them all, but this will show you all the things that automatically run, at least most of them. 25 to 30 registry locations. It's really quite useful, and you'll see something like this. This is one. Here's all these things launching when I boot up: Box Sync, Dropbox, Windows Mail, Google Update, SkyDrive, whatever that was. You know, this is, I think, back in the days of Windows XP or something. But anyway, that's the kind of thing you'll see. That's just what auto runs will do. It'll find all the automatically things that automatically run, or at least a lot of them. Malware, of course, is sneaky and might slip past it, but a lot of it you'll catch. So here's things you might do in the registry. These are API calls. You can open a registry key, set a value, get a value, and sometimes documentation will describe this function, and they will not include the trailing letter, which might be W or A in a call like this, whether you have an ASCII character or you have a wide character, which is Microsoft's 16-bit Unicode. Microsoft is an international language, so almost everything in Windows uses this Unicode. Unfortunately, it is a very, very old version of Unicode, where it's only 16 bits, and every character is always 16 bits. So for English, it wastes half the space. And for foreign languages, it doesn't work very well because there's not enough characters to symbolize the whole Chinese language and Japanese and Arabic and everything. So it's actually a pretty miserable choice, but that is the default for Windows. It's an old version of Unicode. Modern version is UTF-8, which has a variable number of bytes for each character that goes from 1 to 4, so it's much better. English continues to use just 1 byte, and you have enough bytes to represent all the commercially viable languages. But anyway, that's what's going on here. A is for ASCII and W is for Microsoft 16-bit Unicode. All right. And so here you've got, for example, code that modifies registry setting. Here it does registry open key extended wide. So it's going to open this key, which is the run key, software, Microsoft Windows current version run. It's going to open it, and then it's going to test something and jump somewhere. What it's doing here, I think, is setting a value down here. And, you know, I'm not quite sure. But anyway, it modifies registry settings is all we really care about here. You always open key and reg set value. It's probably writing something in the run key to make the malware automatically load, and it's probably testing here to see if it's already there in case it's trying to infect the same box twice, which is quite common, so it won't provide another copy of it, that kind of thing. You can also save what you find in the registry in a .reg file. You can go to File Save As, and that will save whatever you selected here and all the subkeys as a text document in a reg file, and it looks like this. It's just a plain readable file that sets all these registry keys, and this is what you might do if you want to make some registry changes for some purpose. Like one thing you used to do pretty commonly when I was in XP tech support is you would want to put off an update because Microsoft had a big update and it was going to automatically get pushed out, and you didn't want your people at your company to get it until you tested it. So you'd have a registry adjustment to stop the update from going on, and you had to get that put everywhere on the machine. And one way to do it is to make one of these reg files and then either tell people to double click on it or more professionally push it out from the domain controller as a software required update. So the next time they log in, it will automatically install that file on your machine. That's also how you put out things like Office updates and so on. That's the right way to do it. You put it in Active Directory in the domain controller, and then everybody will automatically have it the next time they log in. Anyway, there's still problems with it because some machines are left on, some machines are broken and turned off and come on later. So it is actually a huge problem in enterprises. How do you really make sure everybody has all the updates? And frequently it fails, and then you have a vulnerability where somebody's got the wrong version of something. Anyway, so let's try Kahoot. 7A. And this is one reason why Apple is not big in the enterprise. Apple does not provide any of these features to control what version of things. There isn't even a way to query to see what version of macOS you're running across your enterprise. And that's ridiculous. It's fine for home users, but they don't think about enterprises at all. If you have a company and you have 1,000 Mac users, you really need to know what software have they got installed? Did they put on something bad? Did they jailbreak the device? You know, there's a bunch of things you reasonably would like to know. And Apple just is not there for you. And Microsoft really is. But all the big companies use Windows. But they all use Apple too because the end users love them. So your rich, your powerful members of your company will demand to use Macs and just tell your administrators to figure out how to cope with it. So there's a product they buy to be the Mac domain controller. I've forgotten the name of it, but there's a third-party product they buy to control the Macs. It's actually kind of reproducing something when I started. When I started, there was a thing called Novell NetWare, and everybody ran that and Windows NT Server at the same time because they had different features you needed. And now everybody has an Apple controller and a Windows controller in their network. And they're different pieces of software, and they don't really work together. And yeah, but they do. Everybody's using both of them, and you have to somehow control what they're doing. So it's, you know, yeah,
question,
yeah.
Perhaps maybe then. When we learned autopsy in
Yeah.
class, we were working with registry because autopsy is able to read registry.
Oh yeah, autopsy reads everything. Yeah.
So, is it too far-fetched to think at autopsy as perhaps as an additional tool for malware study?
Well, you don't normally use it, but it's true. It's part of forensic analysis, and part of that is malware. The main reason why you wouldn't normally use autopsy for malware analysis is that it looks at a whole disk image. And that's usually too much information.
Right.
What you usually want is a small amount of information to help you track down the infection. That's why I usually use Velociraptor.
Velociraptor.
Yeah, but I mean, they're very similar, you know, but the point of Velociraptor is to do live collection of a small amount of data, like all the running processes and all the registry keys. But the point of autopsy is to do an in-depth investigation of the whole hard drive.
Yeah.
So that's right, but Jim, they're very similar. They're very similar processes,
right.
yeah.
No, because I'm thinking, I should get the similar information applying the tools.
Oh, absolutely. And this is something my best forensic teacher told me. He uses open source tools and sometimes makes his own tools. And people will argue about tools in court. And he always says, you can use any tool you want, and any competent investigator will find the same thing. That's the right answer. All the tools are doing the same job, really.
Yeah.
They just focus on a different area of it, is what they're good at. Yeah, absolutely. Good. And you know, you could have no tool at all and just use regedit yourself. You know, there's...
Because at the end, it's always to have, a sort of variety of tools that you can
Yeah.
implement.
No, and that same forensic teacher told me when he started, there was only one tool, and it was Norton Disk Editor. It was just a hex viewer. The only thing you could do was look at the whole hard drive in a hex viewer. That's all you could do. And, you know, all the rest is just try to make it more convenient than that. Yeah. All right. Well, let's give it a shot.
Oh, just three, only three.
Just three, so I can already guess who the winners will be. But anyway, such is life.
There are only winners.
Yeah. Well, you miss every shot you don't take. By showing up, you people win. So the pointer to an object. I'm thinking of a handle. There was actually a statement in the lecture that it's not a pointer. I don't know the difference. It's awfully close to being a pointer to an object. Apparently, there's some sense in which it's different, but anyway, that's the best answer to this question. There's probably some subtle difference I don't understand between a pointer and whatever a handle is, but they seem very similar to me.
Well, on the slides you mentioned also the long pointers. Pointers that are pointing to other pointers.
Well, that's true. There's indirect pointers. It might be that. Yeah. Yeah. Anyway, all right, the second stream of data in a file. All right, that's alternate data stream. Good. Wait, which one is a root key? Yep, H key. They all start with H key. H key current user, H key local machine, and so on. Those are registry root keys. All right, and which one is a sysinternals tool? That's auto runs, yep. Those tools are great. We use a lot of them. All right. So then there was talk about networking application program interface calls, and mainly it has, the internet was invented at UC Berkeley. That's why they invented BSD Unix, and they invented the internet. The Unix was made it so machines could talk to each other, and the internet was the way they did it. And so they invented these things called Berkeley compatible sockets, which are the essence of networking. And they had these names, they've had them forever, and Windows just has a port of the standard library. So you create a socket, you bind to a port, you then listen for incoming connections, you then, after you get a handshake, you accept the connection or connect to a remote socket, and then you can receive or send. And these are the standard Linux calls. This is what's called raw sockets, direct connections, where you handle everything yourself, and you could therefore control the TCP handshake and everything else manually. That's raw sockets, which are what you have in WS232. People also call this WinSock libraries. There used to be a site called Two Cows, the ultimate collection of WinSock software, which at least originally I think consisted of stuff that was sort of ported over from Linux. But anyway, it was compatible with this anyway. All right, so those are the basic raw sockets. So on the server side, you have to do a whole bunch of calls. You have to do make a socket, bind, listen, and accept to get a handshake, and then you can send and receive. On the client side, you have to create a socket, connect, and then send and receive. So there's a lot of calls you'll see if you're using raw sockets. And so you'll see them here. You have to run WSA startup to get it ready. Then you can create a socket, bind, listen, and accept. This is what you see if somebody's using raw sockets. And again, this is very suspicious. Nobody doing anything normal would ever use raw sockets. You would use higher level things that connect to the internet and download a file all with one command. Controlling the packets one by one is crazy. The operating system will do a handshake and connect to a server with a domain name. That's what a normal person would do. The only reason you'd use raw sockets is because you're doing something crazy. Some non-standard network protocol, which probably means you're malware. You're sneaking some kind of packets on the wire that are not normal packets. Normally, like I said, the high-level API is WinINet. You wouldn't use WinSock, and then you'd have things like Internet Open URL, Internet Read File. That's what a normal person would do if you're doing a normal task. So again, this is the general trend through all of this course. The malware writers use low-level functions that are harder to use but more powerful, so they can do sneaky things to escape, your detections. So, all right, then we can talk about how you transfer execution. So you want to move to another part of code, you can do it with jump or call, but there are a lot of other ways. The operating systems are all interrupt driven. They're constantly being interrupted and having to do new things. So the progression of execution does not follow linearly down a series of steps at all. They're constantly being interrupted, go do this, interrupt, go do that. And when nobody's interrupting them, they're idle. Everything happens because of a signal, and the signal is like an interrupt. So there's all these different things running, and they each get different chances to run. They each get triggered by some kind of event. So the DILs, of course, are the libraries, the shared code among multiple applications. We talked about this, and they're deliberately written to do something many applications might want. Like we said, the library here, WinINet, will give you these functions, like open a URL, and every program on your machine probably wants to open a URL to save a file or download an update or something, so they all just use the same library in memory and the same call. Right. So that's the game. Now you could do statically compiled code where your code makes its own copy of every library function it uses, and that makes the program bigger and slower to load, but then it runs independently of others. And almost nobody does that in Windows or even Linux these days. It's possible, but it's not a common thing to do because it's more efficient to just share the libraries. More dangerous, though. All right, so using DILs already included in Windows makes it smaller, of course. It's easier to just use the built-in DILs, and you can also make custom DILs, and you can even make them and sell them, and Microsoft intended it for that. So you can write code and sell your code. They wanted to create a commercial business of creating and selling software. That was the purpose of Windows. That's also, by the way, the purpose of Facebook, to sell games and stuff on the platform. They create a platform, and then you can make money by making software that runs in that environment, which people find valuable. That's the idea. So you can put malicious code in the DIL. You can use the Windows DILs, which is living on the land, which is a very popular technique. I was reading another malware group that did this recently. This is increasingly common. You don't use malware. You use the built-in Windows commands or the downloadable Windows utilities like sysinternals, so you won't set off the antivirus. You use legitimate system management tools. And if you know, you can do a lot with them. Maybe you can do everything you need to with them and never use malware. That's a common technique called living off the land. Living off the land, yeah, that's the idea, like where you just catch whatever's around you and live off of that. That's the idea. You don't add any more code to the box. You use the code that's already there. And then, of course, you can use third-party DILs. You can take a common third-party piece of software like Firefox that's on most boxes and use that, and then you might fool people. All right, so DILs are a lot like EXEs. It's very simple. There's just a single flag that tells you if it's a library instead of an EXE. But of course, DILs have many exports. EXEs only export one, which is the entry point. DILs have many entry points, one for each function. All right, so there's processes. Each program is a process. Each process has its own handles in memory, and it has a bunch of threads, which are pieces that can move independently. Older malware ran as an independent process. Newer malware often sneaks into existing processes. They'll have many processes running at once. If you go in Task Manager, you'll see a typical box is running. This one's running 50. This was an old Windows XP, I think. Now it's probably 100 processes running all the time. Of course, most of them are not doing anything at any given time. They're waiting for a signal that it's my time to do something. But, all right.
Forgive me, sir.
Yeah.
If an item is doing anything, exe or DIL, whatever, I notice a change in the CPU, not the memory. Because the memory is simply telling me it's loaded, is occupying this space.
Yeah, it doesn't usually change.
But if it's doing something, the CPU...
Now, it could change if you have a memory leak, but normally it doesn't.
Okay.
Yeah, and the CPU, of course, changes.
So when it changes, they say, oh, wow, this is doing something.
Right, it's been triggered, it's doing something, that's right. So when your machine slows down, I often go here to find out what the problem is and see what's using up all the CPU, and I can decide whether I want to kill it or not. Yeah. And if you have certain kinds of malware, like Bitcoin or cryptocurrency miners, they'll be running on the CPU all the time. You could go here and see them. If they aren't hiding from this, which is possible. And, all right, so that's right to say. They each have memory in each process. Even though two processes think they have loaded in the same address, they all think they're loaded at 400,000. They're not really. The physical RAM is different for each process. They each have their own part of memory that doesn't overlap with any other. They're separate, even though they might think they're using a virtual address that's the same. So you can create a new process, and you have a handle for standard input, standard output, and error. So you can specify what input, output, and error this process is going to connect to, which you might send to a socket if you're making a remote shell or an internet connection, or you might send to the keyboard and the monitor if you want the user to control it. And so here's what the code would like. You have a socket handle here, then you load the startup info. You're going to load this into a structure called process information, and then you're ultimately going to call create process. So this is the standard thing you always have. You're pushing a bunch of parameters onto the stack. Process information, startup info, see all these push commands. You're loading all this stuff on the stack, then you call the function, and it's going to look on the stack, expecting to find all these things set up correctly. And if they aren't set up correctly, it won't have any way to know that. It will just operate based on whatever it finds there. Yeah. All right, and so processes are containers and contain threads. Threads are what actually gets CPU time. The CPU is strobing through the threads. Do you have anything for me to do? Do you have something for me to do? Do you have something for me to do? If not, then I'll wait and try again, and I'll just be idle until somebody has some work for me. So each one of them has a chance to move forward. Each thread has its own registers and stack. And that's why this is called a context switch. Every time I move from one thread to the other thread, I have to save all the registers and the stack pointers so I can move to the context of the other thread, which has different registry values. So you have to waste some time saving the data and then restoring it. That's called a context switch. And if you have, one reason machines run slowly is they're having too many context switches. So that's the thing to know about. All right. And so you can create a thread. There's an API call for that. And so one thing you can do is load a malicious DIL into a process by creating a thread, and then you can create an input-output thread, and then you can communicate with the running application. Mutexes. Now, since we talked about every process having its own memory that's separate from all the other processes, what if you have something you want to tell another program? There is a way to do that, and those are called mutexes. You can have global objects which can be seen by multiple threads. So in the kernel, you call them mutants. In userland, you call them mutexes. You can set a object in a file system which sits there like a handle that is just a mark which can be seen by other processes. So you might put a markup saying, I'm editing this file. Nobody else edit this file right now. It's busy. And malware often marks the box to say, this box is already infected. Don't infect it again. So here's some things your mutex can do. This would give a thread access to the mutex. This will release it so another thread can get at it because the different threads can write data into the mutex. You can create and open the mutex. And here you go. This is malware. This is an example of it. It opens the mutex and then it creates a mutex. So it looks for the mutex to see if it's already there. And if it is, then it shuts down, doesn't try to infect the box a second time. If it's not there, then it writes this thing called HGL345, creates a mutex with that name. That's the kind of thing you might do. All right. Let's take a look at 7B. You can see them in Task Manager. That the thread count is there. Also handles. There's processes, threads, and handles. All there in Task Manager.
And you can kill a thread without killing the whole program, right?
I don't know if you can kill a thread. Maybe with Process Explorer. I don't think with Task Manager. But you can see the threads. You can see the threads in Process Explorer, but I don't know if you can kill just one thread. I've never tried. What's that? Are threads what?
Windows only?
Well, I've only heard of them on Windows. I assume Linux must have something similar. Because I know general structure is essentially the same. They might have a different word for it or something. Yeah, I haven't seen the equivalent of Task Manager on Windows. I've seen TOP and PS, but they don't give you all this detail. There probably is some Linux tool for developers to debug your stuff at this level, but I've never used it. Maybe they don't. It's a good question. An interesting question. I never thought of that. All right, let's give this stuff a shot. So which library has bind and accept? WinSock, and this is version 2, 32-bit, that kind of thing. That's the WinSock library. The kernel is just the heart of the operating system and the device drivers and stuff. But this is the userland library that reaches those features. It, of course, has to call kernel functions to get the job done. All right, which library has internet read file? Which is far more practical, something a normal person would use, as opposed to raw sockets. Yeah, that's it, WinINet. This is the library a normal developer would use. They would not use this, unless you're nuts. This makes it much easier to do a normal internet connection, which is what you normally want. And by the way, Firefox might have something like it, but it doesn't have that exact name. Although I imagine Firefox just uses the internal Windows libraries for things like that, but I don't know. All right, what's the type of file that is like an exe but has one flag value different?
Basically, if we want to turn a deal into an Excel, we modify just the header. Is
Yep.
just the header to be modified?
Yeah, just edit the header. Yep. That's all you'd have to do. It's they're essentially the same. There's only a small difference. Yeah. They're both portable executable files, the same format, with just different parameters set in the header. Yeah. All right. And what's the global object used to coordinate multiple processes? That's a mutex. That's a mark made in the file system that can be seen by other processes so you can communicate with them. All right. All right. All right. Same 3 people, fair enough. All right. So, I see it's 10 minutes to 7. I guess we should take a break before we finish.